Welcome back to the deep dive. Today, we are doing something a little different. Usually, we look at a car and we talk about the horsepower or the 0 to 60 time or maybe the size of the touch screen.
Right, the obvious surface level stuff.
Exactly. But today, we're going to really look through the car. We're going to dive into the molecular revolution happening inside the chassis, inside the foam, and even inside the paint.
It is a completely different way of seeing a vehicle. I mean, we aren't looking at a machine of assembled parts anymore. We are looking at a highly complex material system.
And we have a massive stack of strategic reports here to guide us. We are talking heavy technical documents from Dow Mobility Science, ArcelorMittal, PFI and DR, and WL Gore and Associates. And if there is one single headline from reading all of this, it is that the game has completely changed. If you think you know where the electric vehicle industry is going, these reports are basically saying, think again.
It's a total paradigm shift. And to understand it, we really have to look at where we've been. For the last 10 years or so, if you walked into a boardroom at any major car manufacturer, there was really only one number written on the whiteboard.
Range.
Exactly. Range. It was the range wars. It was this singular, relentless obsession. Can we hit 300 miles? Can we hit 400?
Because if the car couldn't do that, it was just a failure. It didn't matter how nice the seats were or how fast it charged.
Right. But looking at the data now, the industry has effectively won that war. The basic question of can we make it go far has been answered.
Yeah, we are seeing 500-mile EVs hitting the market now. The whole range anxiety conversation is really fading away.
It is. But what these reports are highlighting is that the industry has walked through that door only to find themselves in a much, much more difficult room. We are entering phase 2 of electrification. And phase 2 isn't defined by a single metric like range. It is defined by a brutal contradiction.
The reports call it the trilemma.
The trilemma, or the impossible triangle. If you are an OEM today, a car manufacturer, you are now facing 3 strategic imperatives that usually absolutely hate each other. And you have to hit all 3 corners of this triangle simultaneously.
Let's map this out because this trilemma is basically the framework for our whole conversation today. What are the 3 corners?
Corner 1 is extreme resilience. We aren't just driving EVs in mild climates like Silicon Valley anymore. These cars are going to Mumbai, to the Norwegian Arctic, to the Australian outback. They are dealing with high-voltage physics, monsoon rains, intense dust, and incredibly rough roads. They have to be tougher than any internal combustion car ever was.
So corner 1 is basically build a tank.
Correct. Build a tank. But corner 2 is digital experience. The cabin isn't just a place to sit anymore. It has to be a sanctuary. It needs to be softer, quieter, more high-tech, and more seamless than a luxury lounge.
So build a tank that feels like a high-end spa, which, usually tanks are heavy and utilitarian and spas are delicate and expensive. That is already a massive conflict.
Exactly. And then you have corner 3, which is the real headache for the executives right now.
Yeah.
Circularity.
This is the regulatory piece, right?
It is the regulatory cliff.
Yeah.
We are looking at the EU end-of-life vehicle directive coming in 2030. If you cannot prove that your car can be melted down and turned back into a car, and actually recycled into a new vehicle, not just downcycled into a park bench, you're going to face massive fines.
So the mission is make it indestructible, make it incredibly luxurious, and make it completely recyclable.
Oh,
Or
yeah.
keep it affordable.
That is the trilemma.
Yeah.
And the core thesis of this deep dive is that you cannot solve this by doing what we have always done, which is component swapping. You can't just say, oh, the car's too heavy, let's swap the steel screw for an aluminum one, or the car's too loud, let's add more rubber. That logic is entirely dead.
So what replaces it? Because you have to build the car somehow.
A new strategic logic called material systems engineering.
Material systems engineering. Let's unpack that term because it sounds a bit buzzwordy, but I have a feeling it is crucial to this whole 2026 paradigm shift.
It is the foundation. It's the idea that you stop looking at individual parts and start looking at the chemistry, the physics, and the manufacturing process as one single knot to untie. You don't just pick a material.
Right.
You pick a system that solves a manufacturing bottleneck, a performance issue, and a recycling mandate all at the exact same time.
Yep.
It's a very top-down approach.
It's high-level multitasking for molecules.
Precisely. We are moving from materials just providing physical support to materials driving energy efficiency and ESG compliance. And today, we're going to break this down using a roadmap from the reports. We're going to look at the vehicle through 3 specific dimensions. First, the core, which is protecting the heart of the EV. Second, the cabin, which is that digital sanctuary. And third, the life cycle, which is how we solve that circularity problem.
Let's start at the core. Because if you don't protect the battery, nothing else matters. You just have a very expensive, very heavy brick.
The battery is the crown jewel.
Yeah.
It is the most expensive component in the vehicle. And protecting it is where I found the first major counterintuitive finding in these documents.
I think I know what you're referring to. Because if I went out to the street and asked 100 people, how do you make an electric car better, 99 of them would say make it lighter. And if I asked how do you make it lighter, they would say use aluminum.
Right. It is the standard assumption. Aluminum is the future, and steel is the heavy relic of the past.
Yeah.
That has been the narrative for a decade.
But ArcelorMittal and P. Finder dropped a data bomb in this report that says not so fast. They are arguing that for the battery bottom shield, that armor plate under the car that protects the cells from rocks and debris steel is actually the superior strategic choice.
It sounds completely wrong, doesn't it? But we have to look at the physics and that material system logic. They compared a standard aluminum housing to a solution using something called Martensite 1500.
Martensite 1500, that 1500 refers to the strength.
Yes, 1500 megapascals of tensile strength. This is ultra-high-strength steel. To put that in context, the steel in a standard refrigerator or a cheap older car body might be 250 or 300 megapascals. This stuff is 5 times stronger.
So it is incredibly rigid.
It is. And because it is so incredibly strong, you can fundamentally change the geometry of the design. You can make the sheet of metal razor thin, much thinner than you could ever make aluminum.
Why can't you make aluminum thin? I mean, aluminum foil is thin.
Right, but for structural protection, aluminum is less dense, but it's also softer. To get the same protection against a rock hitting the bottom of the car at highway speeds, the aluminum needs to be thick. It needs bulk to absorb the impact. The Martensite steel is so strong you can use a very thin sheet and still stop the rock from penetrating.
So even though steel is heavier by volume, you're using so much less of it that the weight penalty just disappears.
The weight penalty shrinks drastically, but you gain something even more valuable: space. This is the sweet spot the report talks about. By using this ultra-thin steel wall instead of a thick aluminum wall, you actually gain 5% more volume inside the battery pack.
5%. That might not sound like a huge number initially to someone outside the industry.
In the world of EV engineering, 5% is absolutely massive. That is free real estate. That 5% volume means you can physically fit more energy cells into the exact same footprint.
So by using the supposedly heavy metal, you actually get more range.
You get higher energy density. And you solve the first corner of the trilemma, which is resilience. Steel has superior intrusion resistance. If you run over a piece of scrap metal on the highway at 70 miles per hour, you want that shield to hold. Steel holds better than aluminum in that specific sharp impact scenario.
But what about the third corner? Circularity and sustainability. I always thought aluminum was the green choice because it's so recyclable.
That is another myth the report tackles head-on. Making aluminum, smelting it from raw bauxite, is incredibly energy-intensive. It is basically solidified electricity. The report shows that cradle to gate, meaning from the mine to the factory door, this specific steel solution has a 44% lower carbon footprint than the aluminum baseline.
44% lower carbon. That is a staggering difference for a company trying to hit those strict net zero targets.
And just to put the cherry on top, the cost is 33% lower.
Okay, let's tally that up. It is stronger, it gives you more room for batteries, it is greener, and it is cheaper.
It seems like a total slam dunk.
So why isn't everyone doing it right now? There has to be a catch. The trilemma implies trade-offs.
The catch is the oldest enemy in the automotive world: rust.
Right. Steel rusts. Aluminum corrodes, but it doesn't rot away like steel does in the presence of salt and water.
And think about where this battery shield is located. It is on the very bottom of the car. It is getting blasted by road saltwater, mud, and gravel every single day of its life. Protecting steel in that harsh environment is extremely hard.
And usually painting it is a whole nightmare process, right?
It is a massive manufacturing bottleneck.
Yeah.
The traditional way to protect a steel battery case is the E-coat process. You take this massive metal tray, you dip it into a giant tank of chemicals, you electrify it to bond the paint, and then, and this is the really bad part, you have to bake it in a massive oven.
I have seen footage of these assembly lines. These ovens are huge.
They are massive thermal beasts. They consume a huge amount of energy. They take up valuable floor space in the factory. And if you are an EV maker, Putting a battery pack housing into a 200 degrees Celsius oven is risky if you have any sensitive component sensors or rubber seals already attached.
So the oven forces you to design the manufacturing line in a very specific, inefficient way.
Exactly. The oven dictates the entire process. And this is where the system part of material systems engineering comes in. PFiner and ArcelorMittal didn't just say, use steel. They said, we need a system that kills the rust and kills the oven.
So they invented a new coating.
They developed the sandwich solution. It is an E-coat-free process.
E-coat-free, meaning no oven at all.
No oven whatsoever. It is a 3-layer defense system designed to bypass that thermal bottleneck entirely.
Walk us through the layers. What makes up the sandwich?
Layer 1 is right on the bare metal. It's called Zagnellus Protect. This is a zinc, aluminum, magnesium metallic coating applied to the steel coil itself before it even leaves the steel mill. This provides sacrificial protection.
Sacrificial meaning it takes the bullet for the steel.
Exactly. The coating oxidizes before the steel does. Then layer 2 is a thin organic coating, or TOC. This acts like a primer. But here is the genius part. It cures at low temperatures during the steel production phase. The car company doesn't have to do anything. It arrives at their factory already primed.
So the steel shows up ready to go.
Ready for the final step. Layer 3, which is PFiner, WUPC. That stands for Water-Based Underbody Protection. This is a specialized wax-like coating that is sprayed on, and the real magic is that it air dries at room temperature.
You just spray it on the assembly line and walk away.
You spray it, you let it sit, and it cures. No oven, no massive energy bill, no bottleneck on the factory floor.
That sounds great for the factory efficiency, but what about on the road? If I scrape the bottom of my car on a tall speed bump and rip through that wax, isn't the steel immediately exposed to the salt?
That is the system's chemistry at work. This coating has cut-edge protection properties. It utilizes a galvanic effect. If the coating is chipped or scratched, the surrounding material chemically reacts to heal or seal off the exposed steel area. It prevents the rust from creeping into the paint, which is usually how these things catastrophically fail.
So by rethinking the entire material system from the specific alloy of the steel to the chemistry of the wax, you solve the weight, the cost, the carbon, and the manufacturing process.
That is the raw power of this approach. It is entirely holistic. But we aren't done with the core yet. We have protected the battery from physical rocks and chemical rust. But the reports highlight a much sneakier threat, one you can't even see.
The invisible enemy. We are talking about air pressure.
In a physics concept called Paschen's Law.
I have to admit, when I saw Paschen's Law in the notes, I had to pause. It sounds like something from a 19th century physics textbook. Why does an EV driver or an automotive engineer in 2026 need to care about Paschen's Law?
Because Paschen's Law explains why your high-tech, incredibly expensive car might suddenly die in a car wash.
Okay, that definitely got my attention. Walk us through the scenario. How does that happen?
Well, we have to talk about the shift to 800-volt architectures. With third-generation semiconductors like silicon carbide and gallium nitride, we are pushing massive amounts of power to get those super-fast charging times and high performance.
Oh.
So imagine you are driving on a highway. You are really pushing the car. The battery is discharging rapidly. The motors are spinning. Everything inside that sealed battery pack gets very hot. And what happens to air when it gets hot?
Simple thermodynamics. Hot air takes up more space. It expands.
Right, it expands. Now you decide to pull over and wash the car. Or maybe you drive into a sudden freezing rainstorm up in the mountains.
You get rapid cooling.
Rapid cooling. The air inside that big metal battery box contracts instantly. It creates a vacuum. The pressure inside drops significantly below the atmospheric pressure outside.
So the pack is basically trying to suck air in.
It desperately wants to equalize. But here's the problem. Inside that pack, you have bus bars and connectors carrying 800 volts of electricity. Normally, air is a pretty good insulator. It stops electricity from jumping between bare wires. But Paschen's Law tells us that as air pressure drops, its insulating ability drops too.
So thinner air or low pressure air makes it easier for electricity to just jump across a gap.
Exactly. The breakdown voltage decreases. If the pressure drops low enough inside that vacuum, that 800-volt current can arc, it can jump across the physical gap between components. You get a short circuit and boom, the system shuts down. Or worse.
That is terrifying, just because the car got cold too fast.
Just because of the pressure differential. So the engineers obviously know this. They know they need to let the battery breathe. They need a vent to let air in and out to keep the internal and external pressure equal.
But if you put a hole in the box to let air in, you also let water in. And water plus 800 volts is also a very bad day.
Correct. So they use waterproof vents. Similar to Gore-Tex jackets, it's an expanded polytetrafluoroethylene membrane, or EPTFE.
Problem solved, right. We
Yeah,
have had waterproof, breathable jackets for decades now.
you would think so.
Yeah.
But the report from W.L. Gore and Associates highlights a massive blind spot in the industry. It is not just pure water out there on the roads. It is road grime. It is oil mist from diesel trucks. It is hydraulic fluid. And critically, it is the surfactants in the car wash soap.
Surfactants, those are the chemicals that make soap bubbly and slippery, right?
Yes, and they are specifically designed to lower surface tension. They are designed to make water wetter, essentially. If you get car wash soap or engine oil on a standard waterproof EPTFE vent, it wets out.
Meaning it soaks right through the material.
It soaks directly into the microscopic pores of the membrane. It clogs them completely. Once the membrane is clogged with oil or soap, it stops breathing entirely.
And then you're right back to the vacuum problem.
Exactly. The vent is physically there, but it is choked. The pressure drops, Passion's law kicks in, and you risk an electrical arc. Or alternatively, the pressure differential gets so high that it actually sucks the rubber seals of the battery pack inwards until they fail, and then water just floods in anyway.
The data point in the Gore report on this was honestly shocking. They compared standard vents to their new technology in a real-world durability test.
They simulated these exact conditions. Dust oil spray, temperature swings.
Mhm.
The standard vents, the ones used in many cars on the road today, failed in as little as 500 miles.
500 miles. That is basically the drive home from the dealership and a week of commuting.
It is a silent failure. You don't know the vent has failed until the catastrophic event happens months later. But Gore developed a specific oleophobic, which means oil-repelling pre-filter technology. In the exact same test, their system lasted 140,000 miles.
500 versus 140,000. That isn't a marginal gain. That is the difference between a massive fleet recall and a reliable vehicle.
And again, it points back to material systems. It isn't just a simple plastic hole. It is a multi-layer EPTFE structure that has to manage the physics of airflow, the chemistry of oil rejection, and the mechanical stress of thermal shock all at once. This is especially critical for emerging markets. Think about driving a high-performance EV in India or Southeast Asia.
Right. You have high humidity, intense, dust-heavy monsoons.
Exactly. If your material system isn't robust enough for that specific environment,
Yeah.
you cannot sell a global car. You fail the resilience corner of the trilemma completely.
It is amazing how much engineering goes into the parts we absolutely never see. And speaking of parts we don't see, I want to talk about one more thing in the core before we move inside the cabin. Connectors.
Ah, the humble electrical connector.
There are thousands of them in an EV. And the report from Dow mentions a technology that sounds, frankly, a little gross. Oil bleeding silicone.
It does sound unappealing, bleeding. But in the world of tribology and automotive assembly, it is pure elegance. They're talking about liquid silicone rubber, or LSR.
What does the bleeding actually do?
It is a self-lubricating material. The silicone is formulated with a very specific chemistry so that over time, micro droplets of oil migrate from the inside of the rubber matrix out to the surface.
So the rubber's always just slightly slippery.
Just slightly. And why does that matter? Think about the robotic arms on the assembly line. We call this the shift-left strategy, solving problems earlier in the production process to save time and money.
Okay, so the robot is trying to plug a complex connector into a socket.
Right. And these modern connectors have incredibly complex geometries. They might have 20 delicate pins. They have tight seals to keep that water and dust out. The physical friction is very high. If the robot tries to jam it in and the friction is too high, the part breaks. Or the robot jams and shuts down the line. Or worse, it goes in halfway, looks connected to the camera, but isn't fully seated.
Which leads to a ghost failure down the road when the customer hits a bump.
Exactly. By using this oil-bleeding silicone, you drastically reduce the insertion force required. The connector just slides in easily, the robot works faster, the error rate drops to near zero.
And does it help once the car is actually built and on the road?
Yes, because that micro layer of oil keeps the seal supple. It prevents it from drying out and cracking over a 10 or 15-year lifespan. But there is another crucial layer to the Dow innovation here. Low temperature curing, or LTC.
Why does the curing temperature matter for a tiny connector?
Because of cost and weight. To save money, OEMs want to use cheaper, lighter plastics for the connector housings themselves, things like polypropylene. But polypropylene melts at a relatively low temperature.
And usually to mold high-performance silicone, you need high heat, right?
Exactly. If you tried to mold standard high-spec silicone onto a cheap plastic housing, You would literally melt the housing. It would turn into a useless plastic blob.
So engineers were forced to use expensive, heavy heat-resistant plastics just to survive the manufacturing process.
Correct. But Dow's low-temperature curing silicone cures at a much lower temperature. This allows engineers to mold high-spec aerospace-grade silicone seals directly onto low-cost, lightweight plastic housings.
It essentially unlocks the cheaper material.
It's the key that opens the door to massive cost savings across thousands of connectors without sacrificing the quality of the waterproof seal. Again, chemistry solving a practical manufacturing constraint to enable a broader business goal.
Okay, we have built an absolute fortress. We have the ultra-high-strength steel shield, the breathing oleophobic vents, the self-lubricating low-temp connectors. The core is secure. Now I want to open the door and get inside. Let's talk about the digital experience.
This is where the emotional connection with the driver happens. If the core is about resilience, the cabin is entirely about sanctuary.
Sanctuary, that is a word that comes up over and over in these reports.
Because the nature of the drive has changed. You aren't listening to the roar of a V8 engine anymore. You are likely stuck in dense urban traffic, or maybe the car is driving itself on the highway. The cabin becomes a living room. It becomes a mobile office. It needs to soothe you.
The report talks about visual HMI and a concept called shy-tech. I really love that term, shy-tech.
It is a beautiful design philosophy. It means technology that is completely hidden until you actually need it. We are moving away from the fighter jet cockpit aesthetic with a million glowing buttons and switches.
Right. Now we want clean, minimalist surfaces, wood leather, soft fabric.
But we still need buttons. You still need to know where to touch to turn up the heat or change the podcast. Shy Tech allows for a dead front design. You look at the dashboard and you see a smooth, matte, premium surface. But when you turn the car on or wave, your hand icons and controls glow right through the solid material.
It sounds incredibly cool, but I imagine it is practically very hard to make solid plastic look like a high-res screen.
It is remarkably difficult. Standard automotive plastic like TPO or thermoplastic olefin is naturally cloudy. It is semi-crystalline in its structure.
So if you put an LED light behind it, what happens?
It looks fuzzy. It looks like a cheap glowing blob.
Yeah.
You lose all the crisp definition of the icon. And to compensate for that cloudiness, engineers have to crank up the brightness of the LEDs behind the panel.
Which creates heat.
Heat and energy drain. And that heat degrades the plastic over time. It is a vicious cycle.
So enter Dow's new solution.
Dow's soft TPO. They have fundamentally re-engineered the polymer architecture at the molecular level. They align the crystals in the plastic so that light passes through them much more directly, rather than scattering randomly.
They basically tuned the molecules for optical clarity.
The numbers are really impressive. Standard industry light transmission for these soft dashboard materials is about 82%. This new material hits 91%.
That might sound like a small jump, but in optics, that is a huge leap.
It is the difference between looking through cheap sunglasses and perfectly clear prescription specs. But the real metric the one designers care about is high-definition clarity, which they have pushed to 81%. This allows for that crisp, premium branding or delicate instructional lighting to live completely under the skin of the dashboard. You touch the surface and it feels like soft leather, but it lights up like an OLED screen.
And speaking of screens, we have to talk about the actual displays, because we are seeing these massive pillar-to-pillar screens now in the concept cars.
Screens that stretch uninterrupted from the driver's door all the way to the passenger door, and they are sweeping and curved.
And glass notoriously hates to curve.
Glass is heavy, it's brittle, and it's incredibly expensive to manufacture in complex curves. So manufacturers desperately want to use plastic or hybrid materials for these giant displays. But there is a massive problem with clear plastic in a car. The sun.
UV radiation.
If you leave a piece of clear polycarbonate plastic in the baking sun for 5 years, what happens?
It turns yellow, it gets hazy and brittle. Look at old headlights.
Exactly, it degrades. Polycarbonate or PMA acrylic will yellow over time. That ruins the whole sanctuary vibe immediately. Nobody wants a luxury car with a yellowing dashboard screen. The solution detailed in the report is optical silicone.
Silicone for a digital screen. I usually think of silicone for baking mats or bathroom sealants.
Optical silicone is a fascinating material class. It is as clear as high-grade glass, but it is highly flexible. It can handle the thermal expansion and contraction of a massive curved display panel without cracking. And crucially, it is chemically inert to UV light.
It just doesn't yellow at all.
It stays optically clear for the entire life of the vehicle, and it can handle extreme heat up to 150 degrees Celsius. So even if you park your car in the Arizona sun in July, your display won't bubble, warp, or fade.
So the car looks amazing, the lighting is hidden, the screens are sweeping and clear, but the sanctuary isn't just about what you see, it is about what you hear. And this brings us to the second part of the cabin experience, acoustics.
The acoustic challenge in EVs is fascinating because it is the exact opposite of what we are used to dealing with.
Hmm.
In a gas car, the engine is a giant white noise machine. It masks everything. It drowns out the wind, the tires, the squeaks of the suspension.
You take the loud engine away and you naturally think the car would be perfectly silent.
But instead, you hear absolutely everything else. The noise floor drops out so every other tiny sound becomes prominent. And specifically, you hear the electric motor itself.
The motor makes sound. I thought they were silent.
They spin at 10,000, sometimes 20,000 RPM. They produce this very specific high-frequency whine, usually right above 1,000 hertz.
That piercing mosquito sound?
Exactly. It is tonal noise, and the human brain absolutely hates tonal noise. It is incredibly annoying and fatiguing on a long drive, so the acoustic strategy has to completely change. You can't just throw thick, heavy rubber mats everywhere anymore because that adds massive weight, which kills your range and efficiency.
So you need a smarter, much lighter way to kill the noise.
The report breaks the new strategy down into two distinct pillars: blocking and damping.
Let's start with blocking. This is physically stopping the sound waves from getting into the cabin.
Right. The car body, the metal space frame, is full of hollow structural tubes. The A-pillars, the roof, rails the rockers under the doors. These are basically giant echo chambers. Wind noise and tire noise travel through them like acoustic tunnels right into the cabin.
So you need to plug the tunnels.
Dow's solution is beta foam. It's an engineered expanding structural foam. They inject it as a liquid into these hollow cavities during assembly. It expands, fills every crevice, and seals the cavity perfectly.
How much better is it than just shoving a piece of pre-cut foam in there like they used to do?
They measure it in air leakage. Traditional acoustic baffles, which are often just pre-shaped foam blocks, allow about 97 cubic feet per minute of leakage. Beta foam gets that down to less than 15.
Less than 15. That is a massive difference. You are practically making the frame airtight.
It translates directly to a 20 to 35 decibel reduction in airborne noise. To put that in perspective for the listener, 10 decibels is perceived by the human ear as a doubling or halving of total loudness. So a 30 decibel drop is essentially the difference between sitting in a noisy, crowded cafe and sitting in a quiet library.
Wow. Okay, so that is the blocking. Now what about damping? That is for vibration, right?
Correct. The floor of the car where the battery sits is a big, flat sheet of metal. When you drive over rough asphalt, that metal vibrates. It acts exactly like a drum skin. It hums and resonates.
And you need to stop the drum from ringing.
Traditionally, you would stick heavy bitumen pads, maybe thick asphalt mats, onto the floor to weigh it down and stop the vibration. But again, that is incredibly heavy. The new solution is Spec Hell-X viscoelastic foam.
Viscoelastic. That means it has properties of both a liquid and a solid. It's gooey.
It means it has both viscous fluid-like and elastic spring-like properties. It actively dissipates energy. The specific metric they use to measure this is called tan delta.
Tan delta. It sounds like a college fraternity.
It is a measure of damping efficiency. A high tan delta means the material absorbs the physical vibration energy and actually turns it into a tiny, unnoticeable amount of heat rather than bouncing it back into the air as sound. This Spec-Hell-X foam has a tan delta of 1.51 millar, which is incredibly high for this application. It stops the ringing dead, but without the massive mass penalty of the old heavy mats.
The report also heavily mentions a process called acoustic studio. This seems to connect back to your shift-to-left idea from the factory line.
This is absolutely critical for the speed of modern vehicle development. In the old days, you built a physical prototype car, you drove it on a test track, realized it was noisy, and then slapped acoustic band-aids all over it until it was quiet enough.
Which sounds slow and very expensive.
Dow uses Acoustic Studio to create complete digital twins of the car's acoustic profile. They use advanced software to simulate 60,000 different combinations of foam filler and placement before a single piece of actual metal is ever stamped.
So they know exactly where the resonant frequencies will be and exactly how to kill them before the car even exists in the real world.
Exactly. The result of that digital optimization is a 55% reduction in the weight of the total acoustic package. You get a significantly quieter car that is also much lighter. You solve two corners of the trilemma at once: the luxury experience and the energy efficiency.
That is amazing. Okay, we have protected the core. We have refined the cabin into a quiet sanctuary. Now we have to deal with the absolute elephant in the room, the third corner, the life cycle.
Circularity. This is where the automotive industry is really, frankly, scrambling right now.
We mentioned the EU ELV 2030 directive earlier. 2030 is right around the
And
corner.
it's basically tomorrow in automotive development cycles. It takes years to design a car. The directive is incredibly strict. 25% of the plastic in a new car must be recycled content, and 95% of the vehicle's total weight must be recyclable at the end of its life.
And right now, according to the reports, we have a specific massive problem with one major component, the seats.
Seats are an absolute recycling nightmare. They are what we call a monstrous hybrid.
Why is that? A seat seems pretty simple. It's just a chair.
Think about how a car seat is actually constructed today. You have a heavy metal frame that is wrapped in polyurethane foam for comfort, and then that foam is glued directly to a leather or PVC synthetic skin for style and durability.
It is a complex sandwich of glued together totally different materials.
And that industrial glue is the killer. You cannot separate the skin from the foam effectively at the recycling plant. You can't melt them down together because they are completely different chemistries. The foam is a thermoset and the skin might be a thermoplastic. They don't mix. So at the end of the car's life, millions of these heavy, bulky seats just end up in landfills or they're sent to incinerators.
So if we absolutely cannot separate them, what is the solution?
Monomaterial design. The strategy is simple in theory, but hard in practice. Don't combine materials that hate each other. Use materials that are in the exact same chemical family.
The all-polyolefin seat.
Correct. Polyolefin is a broad family of plastics, things like polypropylene and polyethylene. The radical idea here is to make the entire seat, the structural frame, the soft foam, and the premium skin out of this exact same chemical family.
So at the end of its life, you don't even have to bother separating them.
You take the whole seat, you grind it up into pellets, and you melt it down. It is all chemically compatible.
But wait, can you actually make a comfortable luxury seat out of just plastic? I mean, foam is soft and yielding. Can hard plastic truly feel like a soft cushion?
That is the major breakthrough with a material called infine air. It is a 3D loop structure.
Describe that for us. What does it look like?
Imagine a block made of thousands of tiny, continuous noodle, like plastic springs, fused together in a chaotic mesh.
Yeah.
It basically looks like a very highly organized bird's nest.
Okay, I can picture that. A tangle of plastic spaghetti.
Because it's a mesh of loops rather than a solid sponge, it is actually 90% open air.
Which must be amazing for ventilation and cooling.
It's incredible. The airflow metric for this material is 300 cubic centimeters per square centimeter per second. Traditional polyurethane foam is less than 50. So it actively breathes, keeps you cool. No more sweaty back on long summer drives.
And because it is made of plastic loops and not an absorbent sponge, it is washable.
Exactly. This is a huge deal for the future of robo-taxis or shared mobility fleets. If every passenger spills a large coffee or drops food into the seat, you can literally take a hose and wash the seat out. You absolutely cannot do that with traditional PU foam. It acts like a sponge, soaks it all up, and gets moldy.
And what about the skin? You obviously can't use real cow leather if you want a mono-material, easily recyclable seat.
They use a material called EVO Air. It is a POE or polyolefin elastomer artificial leather. It looks and feels exactly like premium soft leather, but it contains no plasticizers.
No plasticizers. Does that mean no new car smell?
Right. That specific new car smell we all kind of love. That is actually volatile organic compounds, or VOCs, off-gassing from the plastics and glues. It's not exactly healthy to breathe in a sealed cabin. EVO Air removes that entirely. It is odorless, and it is incredibly 25 to 40% lighter than traditional PVC artificial leather.
So it is significantly lighter, it's healthier, it's washable, and it's breathable. But the real key, the whole point of this is the recycling aspect.
The no downcycling promise. Usually when you recycle mixed plastics, the polymer chains break down and shorten. The material gets weaker every time. You take a high-performance car part and you are forced to turn it into a low-stress item like a flower pot or a parking lot speed bump.
Which is fine for waste reduction, but it's not circular. It is just a slow death for the material.
Exactly. It's a delay to the landfill. But with this pure polyolefin system, the report shows that the recycled material after being melted down has less than a 10% change in hardness. It retains its mechanical properties.
So you can literally turn an old car seat into a brand new car seat.
That is the holy grail of manufacturing. Cradle to cradle, you completely close the loop.
But wait, I have one more major question on circularity. 2030 is very close. How do global car companies get enough green recycled material right now to start meeting that 25% recycled content target? I mean, we don't have millions of these new, easily recyclable seats ready to be ground up yet. They are just going into production.
That is a very astute point.
Hmm.
And it brings us to the final piece of the strategic puzzle, a concept called mass balance.
Mass balance. It sounds like an accounting term.
It is essentially accounting, but for carbon atoms. It's a chain of custody model.
Explain how that actually works in a chemical plant.
Let's say a major chemical company like Dow wants to make plastic for a car bumper. They put liquid feedstock into their cracker, which is the massive machine that breaks down molecules to make polymers. Usually that feedstock is crude fossil oil, specifically naphtha.
Okay, standard petrochemical process.
But now they can mix in bio-based feedstock, things like used cooking oil or agricultural waste. Or they can use circular feedstock like pyrolysis oil, made from chemically melting down old unrecyclable plastic waste.
So they just mix the new green oil with the old fossil oil in the exact same giant tank.
Yes. And once it is in the tank, you obviously can't tell which molecule is which. A carbon atom is a carbon atom. So they use a strict independent certification system like ISCC+. If they put 10% green oil into the total mix, they are legally allowed to sell 10% of their final plastic output as certified circular or bio-based.
Why is this approach better than just building a brand new separate green factory that only uses recycled oil?
Speed and safety. Building a new chemical facility takes 5 to 10 years and billions of dollars. Mass balance allows them to use the existing massive global infrastructure today. And crucially, for the highly regulated car companies, it offers no requalification.
What does no requalification mean for the engineers?
It means the physical plastic coming out of the pipe is chemically 100% identical to the fossil version they have always used. The automotive engineers don't need to spend 2 years retesting the crash safety, the flammability, or the UV durability of the bumper. It is the exact same molecule. This has a different certified origin story.
That saves literally years of testing and millions in validation costs.
Exactly. It completely shrinks the time to market. It allows the massive automotive industry to start heavily decarbonizing the supply chain immediately, while the physical recycling infrastructure slowly catches up over the next decade.
We have covered a truly huge amount of ground today. We went from the very bottom of the car with the ultra-high-strength steel shields protecting the battery, to the microscopic EPTFE vents breathing air and blocking oil, the self-lubricating cold-cured connectors, the high-def Shy-Tech dashboards, the silent acoustic foams, and finally the fully circular mono material seats.
And if you step back from all those details and look at the whole picture, you really see the profound shift in the industry. We aren't just assembling distinct passive parts anymore.
It feels very different. It feels highly integrated.
It feels almost biological.
Biologics.
Think about it. We have a skin that chemically self-heals when scratched. We have lungs that actively breathe to equalize pressure and filter out toxins. We have a skeleton that is incredibly light strong and perfectly optimized for impact. We have connective tissue that constantly lubricates itself. And we have a physical body that can be completely melted down and reborn without losing its essential strength.
That is a wild thought. The car is becoming less of a traditional machine and much more of an organism.
And that leads to a very provocative question for the future of mobility. We talk about software-defined vehicles all the time in the industry right now. But if the physical materials are becoming this smart, if the foam breathes, if the skin heals, if the connector adapts to friction, does the rigid distinction between hardware and software start to blur?
Maybe we should be talking about material-defined vehicles.
Or perhaps the material itself is becoming the software. It is programmed matter. We are fundamentally programming the molecules to behave intelligently and adapt to their environment.
Okay, my brain is officially full. Next time you get into your car, take a look at that dashboard. Touch the seat. Think about the tiny vent hiding deep under the hood, keeping everything alive.
Yeah,
There is an absolute revolution happening right under your fingertips.
absolutely. It is an incredibly exciting time to be a materials nerd.
Thanks for joining us for this deep dive. We will catch you on the next one.
Stay curious.